So let's start by reminding ourselves what we did last time. So we were talking about Feynman rules and Feynman diagrams. Feynman rules. And we started with the scalar real phi to the fourth field theory. And we saw these kind of diagrams. For example, this diagram, which we argued is some symmetry factor times the value of this diagram. And the value of this diagram is basically integrating over all undetermined momenta, conserving momenta according to the Feynman rules of the specific theory. In this case, for example, it's dd plus 1 of p over 2 pi to the d plus 1 over the times the propagator. So for example, this is the propagator if this is a 4 momentum. And then I also sent you an email on how to Zvi taught us how to calculate the symmetry factor. So for example, here in this very simple diagram, we basically draw the vertices first and the outer legs, and then we connect. For example, here there are 4 possible connections, so it gives me a factor of 4. Then I connect here, I have 3 options, so it's 3, and then here I have no options. That's the only thing I can do, and therefore this diagram is 4 times 3 divided by 4 factorial, which is 1/2. And I wrote a long note on how, with a few different examples. You can go over it. Then we saw a complex field. So complex scalar fields. I argued that then, for example, the propagator can acquire a direction. Let me write it like this. Something like phi bar would be something like this. And the same story holds there, except then you have to make sure that to count not only connect the diagram appropriately, but also have the directionality fixed. So you can't have, for example, a diagram. You can't have a diagram like this, where they're going into. This is like, you can't have that because you need the propagator to go in a specific direction, and that's just reflecting the fact that psi bar is basically 0. Okay, for example, phi bar, sorry. And then we talked about the Yukawa theory. So the Yukawa theory is where things start to become interesting, because we have our action is something like psi bar g naught to the minus 1 psi plus, say, phi 1/2 probably d naught to the minus 1 phi plus some sort of lambda phi psi bar psi. And I've argued that this is a very general thing. It happens anytime we couple a boson to density. This happens in many situations. One example is electron phonon coupling. Okay, actually, with electron phonon coupling, there are a bit details that need to be discussed. For example, you can either couple to acoustic phonons, which are like density, and then but then there is the coupling constant has some spatial dependence, which is important. Or if you like, the coupling is not to phi, but to the divergence of the displacement u, which is like density. of the ions, but that's a detail. In other words, phonons are vectors, like they're a vector field of displacement, and they're not a scalar field. So that's another example would be, so you need to, like, either you write this as an effective model for electron phonon coupling, or you need to formulate exactly what you mean. And another example would be like the Higgs boson, but it's a very useful toy model to study the interaction between fermions and bosons. And then there are other examples where you can couple the boson, instead of to density, you can couple it to some other fermion bilinear with the appropriate symmetry. For example, if you're coupling to a magnetic fluctuation, let's say phi is magnetism, then you would put a Pauli matrix here, or something to represent the fact that it's magnetic. Yeah, and there are different examples. So it's a well-known result. And then we looked at the boson self energy. Okay, and specifically, okay. First of all, before that, let me first write the Feynman rules. So we have something like phi is a dashed line like this, and psi bar, that's our Green's function. It's like this, and then we have the vertex would be a scattering from some state k to k plus q, and this would be a boson carrying q. Okay, and then we said that the boson Green's function d of q, we can formally write it as a path integral, and that would be a set of diagrams and so on and so forth. And we can think about many other diagrams, but we focus specifically on this diagram, which is what we call the bare bubble. So this bare bubble we denoted it by pi of I omega and q in Matsubara space, and here we have extra minus sign from fermion loop. So this is a general thing that anytime you have a fermion loop, you're going to have an extra minus sign. And this thing, we calculated it, and we found that it's proportional to the electronic density of states. So we expanded this for a specific model where this g naught to the minus 1 is something like I omega minus, say, VF k minus kf. So we're expanding something around some Fermi surface. I'm assuming it to be symmetric. I have a Fermi C and all that. Then in this case, there is a density of states, which is it's basically kf to the d minus 1 over vf. Okay, it's proportional to this with some factor which is related to the d-dimensional sphere, whatever. And then there is this factor 1 minus I omega over VFQ times log of omega minus I VFQ divided by omega plus I VFQ. and then we argued that okay, you know, we can, with the exact same price, we can actually sum up all diagrams. So, you know, these diagrams might be difficult, but we can easily sum up, you know, this plus that. Okay, and this is known as the random phase approximation. And from other techniques in field theory, which we might learn in the future, you can even see that summing up only these diagrams is equivalent to assuming that the bosonic field remains quadratic or harmonic. Okay, so what we get is, I call it DRPA, is basically 1 over d naught to the minus 1 minus lambda squared pi. So pi can be viewed as a self-energy correction to the bosonic propagator. And then we saw from pi, we saw two interesting things. One of them was a mass renormalization. So we saw that this mass here is shifted. And the second thing is that we saw that this thing leads to dissipation. So we did analytic continuation of this omega, and we saw that it naturally leads to a situation where we basically have something like this, where here you have dissipation. Okay, only in this region where this is VFQ, this is Q, and this is omega. And what this represents, this is what we call the particle hole continuum. Okay, particle hole continuum. And what it represents is the region where kinematic constraints allow for a boson with the corresponding omega and Q to scatter on the Fermi surface. Okay, from a Fermi surface, let's put it that way. And therefore, it is dissipated, or it basically, what happens is that the boson propagates, and as it propagates, it kind of generates these particle hole excitations and loses its energy and dephases. Okay, so this is what we can get from this approach in field theory. And now, what I want to do is the complementary picture, which is compute the fermion self-energy. Okay? Any questions about that?
You said boson like scattered. What do you say about the boson and the Fermi surface?
So what these processes describe is basically a boson which is propagating and then spontaneously generating a particle hole excitation. This is this. Okay. So basically the ground state of the system is where all the fermionic states are like that, and then we're looking at the propagator, the correlation function. You know, the correlation function, as we will show maybe this lecture, maybe the next, is actually related to a correlator. Well, we already know it. It's basically a correlation of a small perturbation of the bosonic field at two different locations or something like that, controlled by this thing. So naively, you know, if the Fermi surface and the boson are decoupled, then it's only controlled by this D naught guy. Okay, that controls the correlations of the boson. Okay. But once you have this coupling, then it leads to the fact that it can basically suddenly create a hole and a particle on top of this Fermi sea, okay, which is this process here. And then they kind of propagate and then re-annihilate and emit back the boson. And that's So instead of just propagating freely, it does these processes, and for this reason, these are called polarizations, because in the language of photons, for example, the way we interpret these processes is that the photon is propagating and it polarizes the electronic medium, which is this, and then it reabsorbs it and continues to propagate. And what happens is that these what we find eventually is that this pi has a dissipative term in it. So it means that, you know, if I think about this, like I'm writing this propagator as a propagator of some wave equation or something, I find that actually it's described in this regime here.
Yeah.
It's described like a damped oscillator, which has a lifetime. And the way we interpret this lifetime is that every time you generate these quasi-particles and then they re-emit, you know, you lose some information, you lose some. So the boson is not exactly, you know, coming back at the same momenta. It might decay into different.
But there is momentum conservation. Like
Yeah, there is momentum conservation.
Okay.
But that's because we're focusing only on the part that does conserve. Like we're demanding this conservation, but no one promises us that some of the.
Like the direction.
No, that's some of the boson was emitted into some other excitations. Like in this, an important issue is that we're not following all possible diagrams and all possible processes, right? For example, you know, if I really want to think about all possible processes, then, you know, this can also happen, right? You know, and then something like this, and you know, I don't know, something like this. You know, it never ends. You know, it's like and these are the kind of processes that might happen, for example, in a collider. But we're not focusing on this. We're actually only looking at this, and by focusing or projecting only to these diagrams, we're kind of losing information. It's actually completely equivalent to Fermi-Golden's rule up to this approximation. This is like a Fermi-Golden rule. So it's telling us, if you take the imaginary part, it's like Fermi-Golden rule. So it's telling us, due to, you know, these allowed transitions, what is the rate at which this decays into all sorts of other excitations which we didn't take into account. That's how we interpret this. Okay? Good. So now I want to do the equivalent picture, which is the electron set energy. So as before, we can write the fermionic propagator, right, as 1 over z, the integral d phi psi bar and psi over psi of k, psi bar of k, and then we have a sum over m equal to 0 to infinity minus 1 to the m factorial. Then we have this s phi psi, which is this coupling here, to the power of m times e to the minus s psi minus s phi. Okay, and these, like this thing, it will also lead to all sorts of diagrams, like this diagram. Like this diagram. Okay, and so on and so forth. So let's let's focus on this type of diagram, and actually also this kind of diagram. So we can actually take into account both kinds of diagrams. Instead of plugging in D0, D0, plot in the normalized D. And that means that instead of every D that we put the entire series of all possible polarizations. Okay, is that clear?
Like the meaning of this is like making it more exact in a way.
Yeah, so the point is that we try to, the name of the game here is to try and use perturbation theory to see what kind of effects we should expect. Okay? Eventually, what I'm going to argue, it turns out, for example, that this diagram that we're going to compute here, it will give us something very deep about Fermi liquids, but if you use it in Dirac theory in vacuum, it gives you, for example, the lamp shift that is observed in the hydrogen atom. So the beauty of this approach is that we're not doing anything exactly. We're just computing correlations in a perturbative manner. But sometimes it allows us access to properties which we see in experiment capture the physics. So this RPA approximation, for example, we saw that it can be used to understand this Landau damping process, which is observed in experiment. You can also get the plasmon frequencies from this. You can get Thomas Fermi screening from this. There are many different things you can do with it. And now with this thing, also you can as I've just mentioned, you can use it to get a bunch of physical like phenomena that you can observe in experiment. And then the name of the game is to control the calculation. To ask yourself, for example, why are these diagrams more important than other diagrams? Okay, so one way to do that is just to make lambda very small. So if lambda is very small, you see that the diagrams that I'm focusing on, this one and this one, are the first ones to appear. Even if you do, look at the full expansion, this is the lowest order. So that's one approach, is to look at the lowest order, and then summing up the entire series or not is basically just equivalent, because you're assuming that lambda is very small and that everything is controlled. But there are other techniques to make these diagrams more important. So sometimes you get that specifically these diagrams have a stronger effect due to other reasons. One of them, famous approach, is called large N. Large N approach means that you can imagine, for example, that you enhance, instead of having just one fermion species, imagine that you sum over this and such that you have n fermions like this. And then here you have a coupling like this. So this phi couples to all of these fermions. Then it turns out that, for example, if I'm looking at second order diagrams, then I can compare this diagram to this diagram, right? They're the same order. It turns out that in this limit, this one is much, much larger by a factor of n. Okay, so that's another way to prefer a specific subset of diagrams. And then there is another issue which is related to kind of dephasing. So in these processes, you see the bubble is kind of, there is no interference in the bubble. Here, there is this requires, this is like a boson which emits these electrons. They just propagate and then are reabsorbed. Here you need something more sophisticated to happen. Like one boson needs to emit two electrons, which then emit another boson, and then recollide to create. So these kind of processes sometimes, there are all sorts of effects, like when the boson is much slower than the electron, meaning that its frequency is much smaller than the Fermi energy. It turns out that these diagrams become very small, and there are other ways to control these kind of calculations. And then there is what people do often is they sometimes don't have justification to use these diagrams. They just do, and see what results they give and try to compare them to experiment. We kind of do what we can. But yeah, it's okay. And that was kind of, if you were at the colloquium by Avi Klein, he gave a colloquium like 3 weeks ago, I guess. That was the message, basically. The message is, why does the subset of diagrams exactly that I'm writing down now, why do they work so well for strongly correlated materials where they shouldn't? Because lambda is very strong. And we have some speculations on why that's so. Okay, so let's focus indeed on this diagram. This is called the fermionic self-energy. So this is 1 over z, integral over d psi and phi, psi k, psi bar k, lambda squared over 2. And then we have, so let's give these guys some momentum. Let's say the external ones are k, that's what we're looking for. Okay, and then we can have some internal p, or let's call this k plus q, and then this would be q. Maybe k minus q. Doesn't matter, it's actually the same. So then we have phi of q, phi of minus q, psi bar k minus q, psi k minus q, psi bar k. Sorry. Psi bar k plus q, psi k. This is k, and this is k minus psi of k minus q. So here I've already imposed momentum conservation, but we could have just written it with delta functions and they would lead to this exact result. So the point is that this is like, this describes a process where you destroy the particle at k, create a particle at k minus q, and this is the opposite one. And now the contractions that we're going to make is, of course, this gets contracted with that, and then these guys go outwards. So this guy goes here, and this guy, goes here. No, here. Okay, and now we can try and track the minus signs. So this gives me one minus sign, and then flipping them is another minus sign. So I got two minus signs. Now I need to flip this, I get one minus sign. Okay, then I go through this pair, it gives me overall nothing, and then I flip let's do this properly. So I should get psi bar k, and then I have psi bar k minus q, psi k, psi bar k psi k minus q. So, oh yeah, okay, I see it. So this one I can take over here, okay, and then I need to switch between them. So that gives me two minus signs. So that's the first step. So I go to psi k, psi k, psi bar k, psi k minus q bar, psi bar k. Sorry, what did I do here? Okay. Then I have psi k minus q. Okay, so this guy and this guy have contracted. Okay, and here I have no minus signs because I got two minus signs. Now I'm going to take this through this guy, so that's one minus sign, and then through the other one, so it gives me a second minus sign. So then I go to, I basically get, oh sorry, just, sorry. I take it through this guy, that gives me a minus sign, no other minus sign. So I get minus psi k, psi bar k, psi k, psi bar k. Okay? And then I'm left with psi bar k minus q, psi k minus q. Okay? So now I get an additional minus sign when I flip between these two and contract. So overall, there is no minus sign. As I promised you, because there is no fermion loop, there is no minus sign. Okay? Good. So now we can write this down. This becomes equal to, so I'm going to omit, so these guys just give me g naught of k, and this gives g naught of k. So it gives this g naught k squared. I'm going to omit that. And then I have, and the 2 here. The 2 also cancels with the two ways I can contract the vertex, right? So that's, we said that the factorial is always cancels out. This is a general thing for, Yukawa and QED. There are no symmetry factors. All diagrams come with a factor 1. And then we have an integral d, let's say d plus 1 q over 2 pi to the d plus 1, and then we have d of q g naught of k minus q. So this is basically the object we want to calculate. Oh, and this is proportional to lambda squared. Okay, and this is therefore this promotes us to define this function I omega and q as basically this integral d omega over 2 pi from minus infinity to infinity d dq over 2 pi cubed, and then we have here, in principle, we have d naught to the minus 1 minus lambda squared pi of I omega and q times 1 over I, and then we have omega minus omega plus or minus, doesn't matter, VF of K minus Q minus K. Okay, that's for a Fermi surface. If you have Dirac fermions, then this will be a Dirac, whatever, there will be some trace, but I'm not getting into that.
Why is the construct of phi q, phi minus q gives the propagate of D and not D naught as opposed to the free?
why did I take it to be D instead of D naught?
Yes, but the other
No.
equation. The integral. Before you wrote sig here. Yes.
That's just a decision. So I don't have to. I could put this D naught.
Okay.
So that's exactly the difference. What you're asking me is we could calculate. We could calculate this diagram. Okay, but since we already have pi, we might as well add to this diagram this diagram
Okay.
and this diagram and so on. Okay, it's just
Okay.
actually it's not just the אותו כסף. What I'm going to argue now is that, okay, you can calculate with this D naught, and we might do that, but it turns out that the singular part, like the most interesting effect, comes from this pi. So what I actually want to argue is that 1 over D naught to the minus 1 minus lambda squared pi, okay, this is like, it's like omega squared plus CQ squared plus M squared minus lambda squared pi, okay, and when this, okay, what happens is that at very high frequency, okay, and momenta, the boson is essentially free from the fermion. At low frequency, it's actually dominated by these terms. And I want to focus specifically on the limit where lambda is weak and M is the most dominant effect. This will be equivalent, by the way. We haven't talked about this, but one way to view, like, if we look at this, where's the original theory? I wiped it out. But if you look at this theory, this Yukawa theory, this theory, in fact, means that if I look naively at this theory, it looks like the fermions are non-interacting, right? Because they're free, and the bosons are non-interacting. But it's only that the fermions are interacting with the bosons. But if you think about it for a moment, that means that actually the electrons are interacting with the electrons through the bosons, right? So it's kind of like, I don't know, we don't like to talk to Hamas, okay? But somehow we're interacting with them, right? We're doing it through, I don't know, from Egypt or Qatar or America, I don't know. So the same thing here. And the kind of diagrams, you can imagine that if you want to calculate, if you want to estimate, for example, what is the interaction between the fermions, you can look at correlators. Okay, you can look at amplitudes. And specifically, we can use Feynman diagrams to calculate the amplitude, this amplitude. So this amplitude, it gives us, and maybe in the homework I'll give you in QED to show that for QED, this diagram in the static limit where you take omega to 0, you obtain the Coulomb interaction. So the Coulomb interaction is in fact what happens when we think about two electrons exchanging a photon between them. Now, why am I saying this? Because it means that the limit where this m is dominant is kind of like an interaction that is a contact interaction, constant. Because these terms, they give spatial and temporal correlations. But if we neglect them, it's like we have no spatial and temporal correlations. Okay, everything is a delta function in time and space. And then this pi is what you would renormalize the interaction due to renormalization effects through this kind of process. So I'm saying this in a moment, you'll understand in a moment why I'm saying that. But anyway, what I wanted to argue is that when a pi lambda squared is much greater than omega squared and CQ squared, and this is much smaller than m squared, okay? So in this limit, we can expand. By the way, I forgot to mention that this m is actually renormalized. So I don't know if you remember in the last lecture, we called it m tilde because this diagram shifts, but that's just to, to be consistent. Then we can say that this thing is equal to m tilde squared 1 plus lambda squared pi of I omega and q divided by m tilde squared. Yes, what? You want to say something?
Yes, but isn't it like you're normalizing it? Isn't it like absorbing
Double counting? No.
What's absorbing like the pi?
You're asking about this m tilde, shifting it from m to m tilde. So I'll just remind you, by the way, that m tilde, the normalized math, is m minus lambda squared n of 0, I think, something like that.
Oh, okay.
Okay, and that means I'm taking into account the constant.
Okay.
Okay. So this pi, if you like, you can call this delta pi, if you like. It's only the part that is non-trivial in pi. Okay? And then you can show, okay, that if you plug this guy in, okay, then the self-energy is 0. Okay? So this term doesn't contribute to self-energy. So we only take this way. Okay? Now, if you put in these correlations, you will get some self-energy. But it's less interesting than what this pi has to say. Because this pi has to say something more, a stronger effect. So we end up with this. Oh, by the way, why didn't you stop me? This is bullshit.
Yeah, omega.
This is like omega and k. Yeah, these are fermionic. Okay, so I omega and k. Good. So this thing is equal to lambda squared, a closed integral over the surface of the sphere, an integral from 0 to infinity, dq q squared over 2 pi to the d, an integral d omega over 2 pi from, say, minus infinity to infinity. And then, okay.
Is it q to d minus 1?
Q to the d minus 1. Oh, sorry, d. Okay. And then, okay. So now I want to plug in this part of the diagram. this. So I want to argue that when omega is much smaller than VFQ, what we get is omega over VFQ, okay, times density of states. So that's what we're going to put here. I'm going to put here N0 absolute value of omega VFQ, and then we're left with I omega minus, omega minus omega, omega minus omega minus VF, and then we have this K minus Q minus KF. Okay?
It shouldn't be like 1 or something like that.
1?
There is 1 plus lambda squared on the left.
1 plus lambda squared.
In the like.
This.
Yeah. Where
No. Sorry. As I mentioned, if you
Okay.
plug this part in the self-energy, it gives you 0.
Oh, okay.
You'll see in a moment why, actually. Okay. Okay, we'll see in a moment. Okay, so now we can perform. So this guy gives a non-trivial contribution here. So first thing we write is that K minus Q minus KF is, so there are two terms here. There is the K squared. Okay, so maybe I'll write it. So this is like K squared plus Q squared minus 2KQ cosine theta. Okay, minus KF. Now we're assuming that all K's are on KF. So we assume that Q is much smaller than KF. Why is this? Why does this make sense? First of all, we don't have to make this assumption, but the interesting physics comes from that limit. Okay, so I'm, you can look at the self-energy anywhere you like, and it will give you reasonable results. But I'm focusing on this specific regime, and it's in many cases it's very relevant. But this is what gives the singular contribution. Okay, now we can expand. So I can neglect this. I can take this K out here, and then what I get is something like KF times 1 minus, right, minus Q over KF cosine theta minus KF, right? So this whole thing just becomes Q minus Q cos theta. So that's the first thing I want to mention.
Like you're calculating sigma on K, like near KF or something. Because you said K is like. You basically
Yes. I am looking at sigma for particles very close to the Fermi surface.
Oh.
Okay, that's actually, there is when we go far away. Okay, we will see actually what happens. Okay, but yes, definitely.
Also, like I think there is like m to the 4 missing.
Right.
Okay.
1 over m to the 4th. Yeah. So yeah. Okay.
Mm-hmm.
So now the second thing I want to argue is that the closed integral dsq over over 1 over I omega minus capital omega plus VFQ cos theta this thing gives us well, this gives us some factor related to the dimensionality of this sphere times 1 over VFQ log of I omega probably minus plus VFQ divided by I omega minus VF. Okay? Now I want to remind you that we're looking at the limit. Where did I write this? So we're looking at the limit where the omegas are very small. What?
Small omega minus capital omega? The result of the integral. The right hand. I mean, you have on the left side of the integral there is omega minus capital omega, and the right side.
Oh, sorry. You're right. No. Let me write this. I omega plus VF Q cos theta. Then this guy gets.
Okay.
I want to establish what this integral gives for a general omega, and then I'll substitute this omega minus capital omega. Okay, what's the question? So the point is that what I want to argue is that when VFQ is much larger than omega, and I want to focus on the very low omega limit, this thing just becomes a sine. So it becomes, so this thing becomes when VFQ is greater than omega, this becomes minus I pi over VFQ sine of omega. Okay, and actually I'm going to prove this in a moment for a different diagram that we'll calculate. So if you don't understand why, then just wait. Okay, but here we don't have sine of omega, we have sine of omega minus capital omega. So we have that the self-energy is minus I pi lambda squared over m tilde to the fourth VF squared, the integral dq over 2 pi to the d. Okay, let's assume for a moment. Let's assume for a moment that we're looking at 3D. D is equal to 3. Because now the dimensionality is important. I can't continue without making some assumption about the dimensionality. Then this is from 0 to infinity. This is from minus infinity to infinity.
I don't know if it's important, but if it's 3D, don't you missing like a 2 pi from the Sulamit?
2 pi, yeah, exactly. That's the 2 pi that gives us 2 pi there. And it's 0.
what are we looking for?
No, everything is fine. So now what I have here is a sine. So I have density of states. I have absolute value of omega. And I have sine of omega minus omega. Okay? So the first thing I want to argue is that this Q here has some sort of cutoff. I'm going to assume that it gets cut off somewhere. So this thing gives us by the way, so I had here Q squared, and this goes with the Q, so this gives us lambda squared over 2, which is some cutoff. This integral, I'm not interested in it. And then this diagram, this integral. This integral, I want to argue is that if I draw sine of omega minus omega as a function of, say, omega, then when omega is negative, it's positive, but it changes at omega instead of, so it's basically like this, and here it's like this. Okay? Now I'm going to assume that also this guy has some cutoff, say here and here, cuts off the integral, and then you can see that this integral basically, if I look at this regime up to, say, minus omega, then everything on this side of the diagram cancels with everything on this side of the diagram, because this is an even function. So I'm only left with an integral from minus omega to omega over the absolute value of omega. Okay? And then this integral the integral is 2 times 0 to omega the omega of omega, which gives us just omega squared over 2. But we have to be careful, because what happens when omega becomes negative? When omega becomes negative, then the picture, so this is for omega positive, okay? But if we have a negative omega, let's see what happens when we have a negative omega. So here we have sine of omega minus omega, and omega is smaller than 0, and this is omega. Then we have here the point minus omega. Here we have minus lambda, here we have lambda, and then it basically switches here. So then that means that, and here we have omega. Sorry, this is minus omega and this is omega. Yes? And then this part of the diagram cancels with that part of the diagram, and we get a negative contribution. So what I want to argue is that this comes with a sine of omega. Omega. Okay? So if I sum everything up, what I get is that the electron self-energy, sigma of I omega, becomes minus I pi lambda squared 4 m tilde to the 4th Vf squared lambda squared, and then we have omega squared times sine omega. Okay? And okay, and this expression, okay, and the first thing I want to mention is that, you know, if we've calculated this plus say that, we can then, as Oz said, with the same money, we can, sum up all these things, and we basically get that G is equal to 1 over G naught to the minus 1 minus this sigma that we have here. So this sigma again becomes like a damping term. Okay? But the crucial thing, which turns out to be extremely important, is that this damping, so I can write this thing goes like 1 over I omega minus VF K minus KF minus I gamma of omega. And this gamma of omega, I might give you an exercise also to think about that. This gamma of omega is much, much smaller than this omega in the limit of omega going to 0. You see that? Because this goes to 0 like omega squared, and this goes to 0 linear. This, my friends, is the condition for the stability of a Fermi liquid. Okay? The reason Fermi liquids are stable to a short-ranged interaction, meaning an interaction that is mediated by a massive boson, is exactly this argument I gave you here. And I'll also give you in the exercise to look at the example when you tune this mass to 0. It modifies the behavior of the equation, and then what you get is you will see that then the self-energy, this gamma of omega, it doesn't go like omega squared, but it goes like omega to some power, which is smaller than 1. And I'll also let you calculate then the fermion distribution function, because you know that from the Green's function, we can calculate the distribution function by taking the imaginary part and integrating. Basically, what you'll find is that the Fermi surface exists only when the power of this damping term is greater than 1. And this is it's the same argument that Landau originally did from Fermi-Golden rule, just formulated in this kind of field theoretic approach. And I might even add, the original Fermi-Golden rule argument to the exercise. Okay, so this is like a very important result in Fermi liquids. And then finally, the last thing I wanted to say is that we talked about the lamp shift. Then it turns out that the lamp shift comes from exactly the same diagram. Of course, the physics is completely different because we're looking at different energy scales. We're looking at Dirac fermions instead of, fermions around the Fermi surface and so on and so forth. But it gives the same, it has the same origin. Basically, the fermionic Green's function is modified, and this changes the energies of the fermionic bound states around the potential. Maybe we'll also add that. But for that, we need QED and we need Dirac fermions, which is much more complicated. Yes.
I'm not sure I understood why, because lambda is gamma, so gamma is smaller than omega. Happens what you said.
First of all, you can, in the exercise, I let you do that. Okay. Like you can calculate the distribution function, and you'll find that as long as the power of this, like this frequency dependence, goes to 0 faster than this term here, then the distribution function that you get will have a jump, a finite jump at Kf. And that's the property that we call a Fermi surface. Okay? But from an intuitive argument would be that, imagine that I create a wave. Okay? These are like the propagators of matter waves. Like we're talking about fermions here. Okay? And omega is the frequency and K is their momentum. So imagine that I'm very close to the Fermi surface, and I generate a very small energy excitation, then you see that depending on the energy of the excitation, you get a certain damping. What this expression is telling you is that as you lower the frequency, the lifetime, the lifetime that is relative to the, because what does this omega represent? It represents the time evolution, the frequency, if you like, of this wave with respect to the Fermi energy. So the pole, the pole of the Green's function happens on the Fermi surface when this is 0 and this is 0. So energy is kind of measured with respect to the Fermi surface. So as I come closer and closer to the Fermi surface, then my lifetime kind of starts to diverge with respect to the oscillation frequency. Because think about it, as you could say, okay, omega goes to 0 always. Sorry, gamma always goes to 0 unless you have like a distorter or something. But it's important how fast it goes to 0, because it's not enough that gamma goes to 0 and the omega going to 0 limit, because remember that the oscillation time of this wave also goes to 0 as you take omega to 0. So the real question about damping is like, how many oscillations can I make before it decays, right? So that's the important question. And once you see, once this term becomes larger than that, then these waves become overdamped. And in the other regime, I can do many, many oscillations before I decay. What I'm telling you here is that if you take an arbitrarily low frequency, you will get an arbitrarily long number of oscillations, arbitrarily large number of oscillations before you decay. So it means that these quasi-particles are becoming sharper and sharper excitations as you come closer to the Fermi surface. And this is a very non-trivial statement, because it means that if I take a Fermi liquid, if I take a Fermi surface, and I add to it interactions as a perturbation, they do not destabilize it. Okay? It can stay, again, arbitrarily close. And this argument is important because naively, there is no reason why this free fermion description, which we use, in statistical mechanics, or Drude uses, or Drude, Sommerfeld, or whatever used to describe metals, why it should work in a real system where the electrons are strongly interacting. Now, by the way, I didn't mention this, but the physics here, which is not really easy to see from the diagram, but I will give you in the exercise a way to see it. It has to do with the kinematics here, because you have a Fermi surface, then you're extremely limited into like the kinematic constraints on where you can scatter on the Fermi surface. Oh, is what limit this. Is what limits this frequency dependence. So as you go to lower and lower energy, there's less and less phase space for these excitations to scatter. Okay, I think this is a good time to go on a break. Just to, so you won't say I didn't show it to you, let me write the Feynman rules for QED. And maybe we'll play around a little bit the exercise in the home assignment. So we have d for x psi bar I d minus m psi, and then we have SA SA is d for x, then we have A alpha D alpha. Wait a second, what's going on? Something here is messed up. So I think this should be something like. Okay, let's probably D alpha, D beta, A beta, or something like this. So here, like, you know, x alpha is G alpha beta X beta, right? Something like this. And then we have then we have SA psi. The coupling is E D4X psi bar gamma mu psi A mu. Okay, so we're coupling I don't know if you remember, it was a while back in the course, but when we did the Dirac theory, then we discussed that this is a current operator. So the current operator couples to the gauge field. Okay, and that gives us the following. So we have d mu nu of, say, q, which is typically drawn like this: mu nu. Okay, and q is equal to I G mu nu q squared. Q squared. So this is gapless, and then G of K is equal to this, and then this is I over P slash K slash minus M. Okay, so K slash to remind you is, this is a matrix, okay, and this is like gamma mu K mu. Okay, so it's a matrix. So 4x4 matrix of Dirac fermions, and then we have the vertex. The vertex is something like, we have a mu coming in, and then we have here gamma mu, and we have K and K plus Q, and this thing is minus I E gamma mu. That's what we did. Okay. So this is, I just wanted to write this, מה שנקרא לצאת ידי חובה, because we might play around a little bit with this, okay, in the exercise. So it's a little bit more, so there are two things that I need to mention. First of all, I wrote this in real, with real time, in real time. What makes this a little bit more complicated is the fact that these are Dirac fermions, so there is a matrix structure here, which we didn't have in the Yukawa theory. I ignored that. And the other thing is that these are vectors. So we have two complications: vectors and matrix structure for the fermions. Okay? So we'll play around in the exercise. Now the last thing I want to cover is
Yeah.
yes.
It seems like SA usually has another term.
Yes.
Like the tensor.
Yeah, this G alpha beta should appear there somehow,
Yes.
but it appears incorrectly in my notes. So what is the correct form?
So there is this.
You mean the projector on the transverse component? So
I'm pretty sure, but it's like
one thing I could write is this. I could write A alpha. Okay, let me try and guess. Something like delta alpha beta minus G alpha beta D alpha no, that doesn't. That's a mistake.
Should be
it's
supposed to be the electromagnetic tensor, right?
Yeah. Okay. We know that this is like F mu nu.
Yes.
Yeah. Right. We can just write it like this.
Yes. Yes. Just plug in the definition.
Yeah. We can write something like 1/16 F mu nu, where F mu nu is a d mu a nu minus d nu a mu. Yeah, that's also
Okay.
yes.
that's fine. But you can. But I wanted to write it in terms of A because then you can see the propagator easily. So what?
So it's like a dot to the square root of G minus.
It's what? It's what?
Dot squared G.
Dou squared G.
Mu nu.
You're saying it's like this. It's something like A mu.
Yes.
That's what appears in my note. G mu nu A nu, like this.
Yeah, but also minus the term that you wrote previously.
Minus what was the?
Minus dou mu dou nu of A.
Minus.
Yes. Dou mu dou nu.
Do mu do nu
Yeah. Then.
A nu.
Yeah. Exactly.
Okay, good. Yes. So what this guy is actually a projector. Okay, so then probably here we have a different propagator, right?
What do you mean by dou squared without an index?
One moment. I get G mu nu minus Q hat mu Q nu hat. What?
So there is something about the Landau gauge, Feynman gauge,
Yes.
and then you choose it so it is like what you had.
This.
Yes, it's something.
That's the Landau gauge.
Feynman, I think.
Fine.
Yes, Feynman. Good. Yeah.
Which is what? Remind me?
Like zeta equals 1. Like, what do you mean? What?
No, but it's like it's basically like saying that the longitudinal part is 0.
Okay.
Right? It's basically saying this.
This is Lorentz gauge, but not Feynman gauge. Or
This?
it's the same. This is Lorentz gauge
Lorentz gauge.
because it's Lorentz invariant.
'Cause it's
Maybe it's the same Lorentz gauge.
Oh, it's
I
always
don't know.
Lorentz.
No, Lorentz invariance is by this term here. You see this term makes it.
Because of the gamma matrix.
Sorry, this is not the Lorentz invariance. This has to do with gauge invariance. You're saying that this is Lorentz invariant. Yes, it's
Yes.
Lorentz invariant because it's a scalar.
Yes.
It's a
But it,
scalar. That's true.
and it's called.
But you
Lorentz
see,
gauge.
if this is true, then these terms they fall out,
Yes.
and then you have only that term.
Yes.
Okay, so under this gauge, we can write, okay, so that's what confused me in my notes. You can write something like A mu D squared G mu nu A nu.
What do you
Okay.
mean by this square?
D squared is D mu,
Ah,
D mu.
okay.
okay?
Okay.
Okay, so, thank you. Because the point is that if you look at my notes, the squared looks like alpha, and I wrote it with alpha and beta, and I couldn't understand what I wrote. But okay, so yeah, so we're assuming this gauge, right? Do you concur?
Yes. But yes. Yes, he is also assuming this gauge. But
What?
yes.
But so what is the additional assumption that you wanted to say about Feynman? What is this zeta?
No, that's fine. That's
Okay.
fine.
What is the name of this gauge? Feynman or Lorentz?
Feynman
So-
gauge.
Feynman gauge. I don't know. Isn't it Lorentz gauge? I think.
So let me tell GPT.
I think it's like in Lorentz gauge you can choose Feynman gauge or Landau gauge, something like that.
Maybe the Lorentz gauge is only related to. I'll tell
That's
you what.
fine.
Maybe Lorentz gauge is traditionally doesn't include the time dependence of A, or the as a 4. You see, A here is no longer like a 3-dimensional vector,
Yeah, it's from
and obviously
from-
Lorentz defined the Lorentz gauge for the 3-dimensional vector. So probably a Feynman gauge is just the Lorentz gauge, but in a 4-dimensional space.
Maybe.
ה-GPT קורא לזה כאילו לורנס.
אוקיי.
לא יודע חשוב, זה סתם שם.
Okay, never mind.
Yes.
Okay, Lorentz. Lorentz is with a T?
Yes.
Okay. Good. So that's that basically allows you to make computations, but this theory is much more delicate than Yukawa theory because it has gauge invariance, and we know that gauge invariance has to be conserved, and it turns out to be a headache because you can compute all sorts of diagrams and processes that will break gauge invariance, and then you can spend time say, oh, maybe the theory doesn't work, maybe gauge invariance is not true, maybe it's broken. But then after a while you figure out that you forgot this diagram and that diagram, and everything conspires together to restore gauge invariance. So it's it's all this perturbation theory is much more dangerous when you have these gauge invariants. It's something to keep in mind. And the way to properly do that, so that I'm staying away from that because, as I've mentioned at the beginning of the course, I'm not really an expert in quantum field theory, but we might play around with it in the exercise. Okay. Now the last thing I want to talk about is disordered systems. So I want to argue that these Feynman diagrams and perturbation theory, they can help you deal also with a disorder potential. So you could imagine, for example, a theory which is something like psi bar g naught to the minus 1 psi plus a sum over q uq rho q psi bar k plus q psi k. And this is a special type of theory because, as opposed to all the Feynman rules we had before, here we do not need to impose momentum conservation. Okay? At least not on the fermions. Also, another property is that this coupling here is not really a field. Okay? It's not a field that we're integrating over. But we're still going to add it to our diagrams in order to follow this absent momentum conservation. So we're going to allow these impurities to absorb momentum. Now, what is this UQ? So the point is that we're basically assuming some disorder potential which is a sum over some sites j equal to 1 up to ni. Okay, these are the impurities in the system, and each impurity has a potential u of r minus rj. So, or maybe let me write rj. So this capital RG is the location of the impurity, and each one of them has a potential. And therefore the Fourier transform, right, of VQ is basically UQ times rho Q, where rho Q is a sum over j equal 1 to ni e to the minus iq dot rj. So these phase factors shift the impurity potential to the locations where it should appear. So now let's say we want to compute, so we can of course compute many things now with this theory, but let's focus on the electronic Green's function. So let's compute the electronic Green's function. So g of k is equal to 1 over z, the integral d psi bar psi, psi of k, psi bar of k. Then we have sum over m equal to 0 infinity, 1 over m factorial. And then we have a sum over q and k, uq, rho q, psi bar, k plus q, psi of k to the power of m, e to the minus s0. And s0 is the free part of the theory. So this part is L0. So, for example, so the point is that these are quadratic terms in psi, so they become extremely simple. So, for example, the term of order n gives a diagram that looks like this. So we have k incoming, and here we have the impurity. And then this continues all the way to the last impurity. So this is something like k, k1, k2, k3. Then here we have km, km minus 1. And then here we have, this is basically u of K1 minus K times rho. Okay, let me call this tilde to make the notations short. Let me call this thing U tilde of Q. Okay, so then I have here U tilde of K2 minus K1, and here I have U
I think you
tilde
already call it like VQ.
VQ, yeah, whatever.
Okay.
Okay, VQ. Fine. V of K3 minus K2, and this is V of Km minus Km minus 1. Okay? So this is the diagram, okay? There's not much we can do with it. It's not bringing us to any meaningful result. And the reason is because there really isn't much intelligent to say about a single realization of the disorder. Okay? Because a single realization of the disorder could be very atypical. And we need to specify exactly the location of the impurities. But what we can do is we can, instead of looking at G, we can look at the average G. G of K average. Which means that we divide by the volume an integral and take an integral, 1 over volume to the Ni. What?
Why are you treating VQ like a field? It doesn't have.
No, I'm not. I'm denoting it because, so that's what I was saying before, that this theory doesn't have momentum conservation. Okay? But in order to follow where this lost momentum goes, I put it inside this field. But this field is, like you said, it doesn't have a Green's function of its own. Okay. So then I have this times pi d3, say, rj. J is from 1 to ni, g of k. So I'm basically, what I'm doing is I'm averaging over these impurities. I'm assuming that every impurity has the same potential, but the positions are just randomized.
You are averaging over all possible positions.
Yes.
Okay.
But this is not the only way to go. Okay, we could have equally assumed something about the potential itself. For example, many times what people do is they assume that the potential itself is like a Gaussian field, which is at every location it also has a different value and it has some variance. It wouldn't modify the results at all. So you can average over position and the amplitude of the impurity, and each one of them can have a different. So this can matter for like small details, and it's important to discuss for a moment. This kind of potential is, let's assume that we have a specific impurity in our system. Let's say, we know how to grow these silicon wafers for electronics in computers or whatever, and we have a very, very typical impurity that appears a lot. I don't know, like we have a lot of argon in the cell that we're growing, and therefore we have a lot of argon impurities, and they just repeat themselves again and again and again, and then we have like a typical impurity. But then you could also have something else, like imagine, for example, you're looking at a two-dimensional electron gas, like, I don't know, maybe graphene, and it's sitting on top of a substrate, and inside the substrate we have impurities, and these impurities are like at different distances from the surface, like some of them are close, some of them are more distant, and then the potential landscape looks more random. Okay, it's not just random positions, but it's really like some random function, and then you might want to treat it differently. So you need to think about exactly what you're doing, and this physics goes into how you perform these averages. Okay, but you can do it. So for example, you could add to this an integral. We could add an integral like d. I don't know, like du. You know, e to the minus u squared over some width sigma squared or something like this. Okay, we could average over u as well, and that's just a comment. But for our purposes, this will be enough.
So averaging on like the like J. So you're not looking at a specific problem with specific RJs. You're averaging all of them.
Yes, I'm averaging over all possible.
Okay.
Okay. It's like imagine that I compute this for a specific realization, and then I compute it for another realization, and then I compute it for another realization, and so on and so forth, and then I average over all of them, all of the behaviors. And there's a hidden assumption here, which is known as self-averaging, that in the limit where you have like a huge amount of these impurities and you're looking at thermodynamic sample, then averaging over say space in a specific realization, it's equivalent to averaging over disorder realization and stuff like that. And then you can get into a whole discussion on when the self-averaging works and when it doesn't work. But the honest truth is that right now I'm just, I'm saying what I'm doing. I'm trying to make whatever general statement I can. Okay, and then you can discuss. It's very interesting what can cause, a real sample to deviate from self-averaging effects. Okay? But at least we need to understand what the average behavior would be. Okay, so now you can see that in this average, the only thing that's really affected by the averaging is this rho. So let's discuss for a moment what is a rho q average. So rho q average is like ni over omega, the integral d3 rj of e to the minus iq rj. So the way one moment. Okay, let me first write. So this thing gives the density of impurities times delta Q and 0. That's the first statement I wanted to, or maybe I can write delta Q. But there is one thing we want to fix here. So yeah. So the point yes, so first of all, do you have any objection to this expression? Let's see, we need to put this and then perform ni integrals like that on this sum. Now I think the point would be that for most of these, so for each one of these expressions, only one of the r's appears, and then we just have, for all the other r's, we're just integrating over the entire space. So this cancels this power, except for one, where for that specific one we get this delta of Q, and then we sum over, and we have J terms like that. sorry, we have ni terms like that. So we're summing over all of them, and we get ni over omega gives us the density. That's the claim.
But the units doesn't work. You have like
The unit
volume over
doesn't-
volume, it's unitless. Before you solving the integral, just the
It's
integral
unitless.
expression.
Okay, so sorry. So this is probably like this. You're right.
Okay, that makes sense.
No, but now it's still okay. So this has to be a delta function, like a colonical delta.
Yes.
If we want to make it into a real delta, then probably we need to put a volume factor here. Volume. Then you can ask a volume of what? I need to think about that.
I'm not sure why we have just omega and not omega to ni. Just some.
Let's see,
Oh, I see. Okay, I understand.
because we have ni integrals like that.
Okay.
Which one?
And then
When you sum ni, you have a sum of ni integrals, which each integral has ni
yes.
coordinates.
That's because if you open this sum up, each time a different rj takes the role of being this integral, and all the rest just gives you omega to the power. And then you can ask about rho q, say 1, rho q2 bar, which you say like we can do so for a general like m order diagram, we would have m powers of this rho q.
Okay.
But here I'm looking at, so this is relevant to say m equal to 1, this is relevant to m equal to 2, and so on and so forth. And here basically we have, this is like a sum over 1 over omega. Okay, maybe there is no 1 over omega here. Sum over ij e to the minus I q1 dot ri e to the minus q2 dot rj, and this whole thing is barred. And then we have two types of terms. We have the first one is when I is equal to j, and then we have e to the minus I q1 plus q2 dot ri plus I not equal to j, and then we have, and this is barred, and then what?
This is we know. We computed.
We already computed it. Yes. Good. And then the other one is just the minus I q1 ri e to the minus I q2 rj, which you could say we also to some extent computed. Maybe I'll actually continue this all the way to the end. And then the argument is that the first term is exactly like what we already computed. It's just ni times delta of q1 minus q2, right? Because it's like the sum of them is 0. And then the other term is like ni squared times delta q1 0 delta q2 0. Okay, so this is how we get more and more terms, and now this allows us, for example, to calculate the second order diagram. So, for example, if I take this Green's function, okay, so let's let's start even before that. Let's start from the first order diagram. So the first order diagram, which we had, which would be something like k, and then k1, And then here we have V. Oh, so we called it V of K1 minus K, right? And say we take an average over that. Then it's exactly related to this sum here. And then I want to argue that what we basically have is just V of 0. And then here we have K, and here we have K. So this diagram gives us, if we look over there, it gives us Ni, U of 0. I think, okay, don't be קשוחים איתי, but I think we need a 1 over omega here just from the Fourier transform. Okay, I want it because I want to get Ni over omega here.
Okay.
And then U of 0, and what else do we get? That's it. Okay, and that means that now we can calculate, this plus that plus that, right? Plus ta 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 ta. And now our Green's function became 1 over G naught to the minus 1 minus Ni over omega times U0. And what this term tells us, this is basically just a constant. Okay, and what this constant is giving us, it's giving us a shift in the chemical potential. And this makes perfect sense, because imagine that I put in my sample, I put many impurities, okay, at many different locations, and now I'm averaging over all their positions. So it's like smearing this potential. Now if everyone gives me U naught, then this potential is suppressed by a factor which is the density of these impurities. So instead of having potential, say, of strength U naught, I get a potential of U naught times the density of these impurities. So if they're very dilute, then the overall shift will be very small. Okay? And it's an effect that it's just like a chemical potential shift, which will mean that it's not interesting. Yes?
Don't you have understand the fermionic property?
I have the fermionic property. G.
In the upper there.
This one.
This, yes.
Yeah, okay. Okay, let me answer your question. So, naively, what you really have here. So, let's be honest now. So, in this diagram, where this is U0, you have a G naught of K times U0 squared times U0 times Ni, the density of impurities, right?
Yes.
So that means that if I draw this plus that plus that, okay, then, by the way, this comes from m equal to 2, right? If I draw all of them together, then I'm going to have G naught of K plus G naught of K squared times U naught plus G naught cubed of K, right?
Yes.
Times Ni times U naught squared Ni squared, and so on.
Yes.
And then when I add them up, I'm going to have G naught of K 1 minus G naught of K times Ni U0, which is 1 over G naught to the minus 1 of K minus Ni U naught.
Oh.
Okay? So, but the reason I wrote this so quickly is because I thought you guys are already experienced with this, because this is like the third time we're computing a self-energy. We did it for the bosons, right, in the Yukawa theory. We did it for the fermions in the Yukawa theory, and now we're doing it for fermions in a disorder potential.
Yes.
Okay? What this means is that the impurities are shifting the chemical potential. Okay? And maybe I got one of the signs wrong, but I don't know. But the point is that this shift can be absorbed in the chemical potential. Because remember that the chemical potential to begin with is a Lagrange multiplier, which we are using to fix the density. Okay? So it really has no meaning to shift the chemical potential. Another thing which you will often encounter in the literature is that people will tell you that they're assuming that this U0 is 0. Meaning that on average, the potential that each impurity generates is 0 on average, just to avoid this thing. Okay? But it's an uninteresting contribution. Now let's look at m equal to 2 contribution. So at level m equal to 2, we basically have, so I'm writing this. So I have K, K1, K2. What is U of K1 minus K, and this is U of K2 minus K1, and I'm performing this average. Then I basically have two types of terms. I have Ni squared over omega squared times U0, which comes from this term here, okay, plus Ni over omega times this term, which is a sum from, say, K, P, and K. And then I have here a U of K minus P, and then U of P minus K. So what I have here is this guy, K, P, K, and then this gives Ni sum over P, U of P minus K squared G naught of P. Okay, so now let's compute this for a Fermi liquid. So let's see what happens to a Fermi liquid when you add a disorder potential to it. Okay, then this diagram becomes Ni. Okay, so now let's assume that U of P minus K is equal to U. What this means is that we're thinking of a disorder potential that scatters to from any P to any K with the same amplitude. Okay, that's the meaning of this thing. Then we get that sigma of I omega, which is this diagram. K, P, K, U, U. This thing is just Ni U squared, the integral d3p over 2 pi cubed. So we're doing this in d equals 3. Okay? And notice here that this is very different from the usual Feynman diagrams. Remember that in the usual Feynman diagrams, any undetermined momenta we would integrate over. That included frequency because we were talking about 4 momenta. But here, because this field, you see this field is static, okay? then these sums here do not include frequency sum. Okay, there is no frequency sum because this is elastic scattering. Okay, why is this true? Because this field here, it's not a field. There is no field. If we want to have a sum over frequency, it's important to have here like a propagator which we're integrating over. Okay, so if for example this was a dynamical field, like a phonon, like the Yukawa theory, then we would also have propagators for the phonons, and we would have some dynamical contribution. And as I've argued when we obtained the path integral, right, the dynamical contribution is related to quantum fluctuations. So the fact that these impurities are just static, like potentials, is all is the reason there is no frequency sum. And then we have 1 over I omega plus Vf p minus kf. Then we can do the integral over all the angles, and we're left with ni u squared n of 0, the integral from minus infinity to infinity, the epsilon over I omega minus epsilon. Oh, sorry, here it's minus. And here I've substituted the integral over p with the density of states times an integral over epsilon. And this integral is very similar to the integral we already did earlier. But now let me show you why this integral gives sine of the omega, or I pi sine of omega. Yes.
You change the sum of all p to integral.
I changed the sum what?
Where did the integral of p?
No. So that's what I was saying. This integral has an angular part, which contributes to the density of states. So the density of states, to remind you, is like kf squared over 2 pi squared Vf, which, for example, in a parabolic dispersion would give you m kf over 2 pi squared, right? Which is the result that you know in lab for parabolic dispersion. Okay?
Mm-hmm.
And then I changed the integral dp with an integral d epsilon over Vf.
I mean,
that's where you got that Vf.
Yeah, I meant the previous integral, like the over p, like, but why are you?
Why am I integrating over p to begin with?
Yes.
Where did this integral come from?
Yeah.
This integral came from
The summing.
The constructor.
So here, now imagine that I'm taking m. Okay, let's write this explicitly. Okay,
It just came from the sum. That's what.
it came from this.
Okay, fine.
But now you see, I'm going to average over rho. That's gonna kill, the.
Yeah.
So I have here 2 sums over q and 2 sums over k.
Mm-hmm.
Okay,
Yeah.
but after I average over rho, and I average over these guys, these internal guys, I'm ending up with only this internal sum here.
Okay.
Well, when you're changing to integral over the energy, why are you integrate over negative energies as well, not from 0?
Because we're doing everything relative to the Fermi surface. So the excitations, right? If you think about this thing, it represents the energy of an excitation. Right? We have something like a linear dispersion.
Okay.
Here you have the Fermi surface, and then you have, you can. I'm not talking now about conservation of particle number or whatever, but you can create a hole here,
Okay.
which has sorry, you can fill a state here which has like negative energy, or you can fill a state here which has positive energy.
Okay.
Okay. Now, if you're concerned about, for example, where the the Pauli exclusion principle is going, then you could imagine, summing over this omega would give you the distribution functions, which in thermal equilibrium would fill everything below and so on and so forth. But here we're not summing over omega. We're doing this per omega.
Okay.
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 Yeah, it's okay. This is the beauty of like field theory. We're computing this diagram in a field theoretic approach, and later on, like I don't know, like all these effects will be taken care of. If you'll compute whatever you'll compute with this. This omega will when you sum over it, will take that into account. It's kind of like when you do a quantum sum and no one promises you that it has to be on shell or something.
And another question, you define u p minus k as u, and then you integrate over p, but you're leaving it outside the integral.
What?
אחרי למעלה הגדרת u של p פחות k.
Yeah, that's the point. The point is I'm assuming that this is basically like assuming that each impurity is like a delta function in space,
Okay.
and then it has no structure in momentum space. What I'm assuming is that it scatters. I could easily put this in the integral, but then I wouldn't. I would have to choose a specific structure.
Mm-hmm.
But just to get to some result in this class, let's assume that it's like a delta function in purity.
Okay.
Okay, so now how do you compute such an integral? This is a very easy integral to compute, right? Because what we have is we have two situations, like if omega is larger than 0 or if omega is smaller than 0, right? If omega is larger than 0, so this is like the integral over, so let's say the real part of z is what we call epsilon. So this is epsilon, if you like. And our original integral is going along this line. Okay? And then if omega, let's see, if omega is greater than 0, then we have a pole here. If omega is smaller than 0, then we have a pole here, right? So this is like I omega, and this is like minus I. Well, it's still I omega, but it's on the negative. Okay. So now what we can do is we can say, okay, if this is the case, I can always complement the integral. I can make
the reason to pull.
What?
You can complement with the reason to pull.
Where there isn't a pole.
Does it?
What?
The question is, does it go to 0?
It goes to, well, you know from Cauchy theorem that this integral is 0.
Yes,
Both
I meant the integral, like the half circle.
The half circle. Okay, let's see.
Yeah.
Let's see. So what I want to argue is that let's focus on omega larger than 0. So then we have an integral like this. Okay, dz over 1 over so let's denote this thing. Let's call this I of omega. Okay, so this thing We have I epsilon. Oh, sorry. Not this thing.
Epsilon integral.
Yeah. Let's call this I of omega. So what we have, this thing is on one hand it's equal to 0, but on the other hand I want to argue that it's equal to I of omega plus this integral. So let me write it explicitly. I actually prepared the other one, but it doesn't really matter. But you guys will help me out because you guys are sharp. So I want to have, so I have this thing, which is r e to the, so along this contour here, z is equal to r times e to the minus I theta. You agree? It's kind of going like that. Good. So dz is minus I d theta times r e to the minus I theta. That's agreeable? So then so this second segment is equal to the integral from 0 to pi minus I r e to the minus I theta d theta of r, wait a second, sorry, I omega minus r e to the minus I theta.
Will we take r to infinity?
Yes, limit, good, thanks, I of omega plus limit of r going to infinity. Okay? And now the point is that this thing is finite, right? Because in the limit where r goes to infinity, this cancels with that, e to the minus I theta cancels with that, and I just get a minus I pi. So I get that I omega is I pi,
Which is independent of omega.
Yes, independent of omega.
It's minus I.
Yes. It's minus I.
Because you switch. Okay.
Minus I. Good. Thank you. Okay? But what happens in the other case? In the other case, omega smaller than 0, you see, then z is equal to r e to the I theta, and dz is equal to I d theta r e to the I theta. Okay, so if I plug that in, I'm going to get that I omega is equal to I pi. So I conclude that I of omega is minus I pi sine of omega, and therefore I get that sigma of I omega is equal to minus I pi ni u squared n of 0 times sine of omega. Okay, and we can actually rewrite this as, so it's conventionally written as minus I sine of omega over 2 tau, where tau is 1 over 2 pi ni n of 0 u squared. And this is the lifetime of the fermionic quasi-particles. So what the interaction couldn't do, the impurities do just like that. So they destroy the quasi-particles. Okay? So actually, disorder does destroy the Fermi surface because we get a finite lifetime which doesn't go to zero and the limit of omega going to zero. Okay. This is what?
It's a bit weird that it appears only in the second order. I mean, I put in a disorder, it's by definition עושה דיסיפציה כאילו. קצת מוזר שזה רק בסדר השני.
Why?
I don't know. It's weird because by definition this is what dissipation should do, and it appears only in second order correction, not in first order. Maybe it's not weird. I don't know.
I'm trying to think about what you're saying.
כאילו אני בהכרח גורם להם לאבד תאנה, הם אמורים לעשות דיסיפציה, אבל אני רואה את זה רק בתיקון מסדר שלי.
So the reason you only see it in second order is because we averaged. Okay. So that's what I was telling Tzvi in the break. Maybe we could think of a wave equation. Like maybe instead of thinking about electrons in a disordered medium, we can think about waves propagating in a random medium, like a wave equation. And then we could maybe we could also add this to the exercise. It could be a nice exercise. Then what we're going to have is what are we going to have? I need to think about it for a moment. So we could let's try and devise that. First of all, how much time do we have? What's the time? No time left. Okay, so I'll try and think of an exercise, but I know, I don't know how to write it right now, but I know that it will amount to the same problem. So we'll have something like a wave equation, but then there's also going to be like potential that couples linearly to these waves. So naively the equation is completely linear, but the disorder is going to be random. So position is no longer going to be a good quantum number. So you can try and do a Fourier transform in average, but then you'll have to assume something about your Green's function. And then I'll write you an exercise.
This is like תהליך ווינר כזה שהממוצע הולך לאפס, אבל במומנט השני רואים את
Yeah, it's actually Schwinger-Dyson, something like that. Schwinger-Dyson series.
But we always did the Dyson series. That's your point in the geometric sum, right?
Okay, that's a Dyson series, but specifically for waves propagating in a, maybe it's not called Schwinger. I don't remember. It's Schwinger-Dyson.
Okay.
Is like the name for a wave propagating in a random medium, and then okay, you'll see. I'll construct an exercise. Okay.
Yeah.
So this is like the average dissipation.
Yeah. This is this whole expansion. Everything we did for disordered system is a statement about the averaged correlation function. So I don't know what to say about a specific correlation function, but if I average over all correlation functions, this is the result.
יש לי שאלה אגב, אבל דיסיפציה.
כן.
תכף
דרך אגב, זה לא דיסיפציה. השם הנכון לתת לזה זה דיפייזינג. האמת. כי דיסיפציה, כשאנחנו אומרים דיסיפציה אנחנו בדרך כלל מתכוונים לאיבוד אנרגיה, ופה כל הפיזורים הם אלסטיים, זה חשוב. אז מה שבאמת קורה פה זה דיפייזינג, זה דיפייזינג טיים. אנחנו שואלים, אלה גלים, אוקיי? האלקטרונים במקרה הזה, זה שהחלקיקים האלקטרונים, אני יושבת עייפתי ואני זקן, במקרה הזה העובדה שהחלקיקים האלה הם אלקטרונים זה סתם נתון סטטיסטי, זה באותה מידה